Hello everybody. So today we're going to do some more equilibrium calculations. We have three examples we're going to do today. We're going to calculate K, we are going to calculate concentrations at equilibrium, and we're going to calculate the equilibrium concentrations using the quadratic equation. So let's start off with our first example on how to calculate K. At a given temperature, 0.1 moles of hydrogen gas are mixed with 0.1 moles of iodine in a 1 liter flask. Calculate K if at equilibrium the concentration of iodine is 0.020 moles per liter. Let's begin by calculating our concentrations. We want to do an ice chart, but we remember that we cannot calculate anything in our ice chart unless we have it in concentration values. So let's start off with the hydrogen and the iodine concentrations because they're giving us moles in a certain amount of volume. So the concentration of the hydrogen is actually going to be equal to the concentration of the iodine because they're both at 0.1 mole per liter, or excuse me, 0.1 moles. So take your number of moles and divide by your volume. So our concentrations are 0.1 moles per liter for our two reactants, hydrogen and iodide. Let's do our ice chart now. So write your balanced chemical equation. So here we have in our ice chart, we've got the initial amounts, the change, and the equilibrium. So let's start off with the hydrogen gas. We already calculated that the initial concentration of the hydrogen gas is 0.1 moles per liter. And that is the same value for the initial concentration of iodine. We'll assume that we have no product to begin with. So we'll put a 0 in the initial part of the hydrogen iodide. So now, the other piece of information that the question gives us is that the concentration of iodine at equilibrium is 0.020 moles per liter. This value, fortunately, is already in moles per liter, so we don't need to calculate it. So let's put that in our ice chart here. Now, as soon as we know two values in our column, then we can calculate the remaining ones. If we had 0.1 mole per liter of iodine to begin, and we have 0.02 at equilibrium, that must mean that 0.08 reacted. So we're basically subtracting here. We put a negative value for the iodine because it is being consumed. The hydrogen is going to be the exact same amount. And the reason for that is the ratio here is a 1-to-1 ratio. Remember, in the change row, that's where we take into account the ratio from the balanced chemical equation. So, if we have 0.08 of the iodine reacting, we must have that same amount of the hydrogen reacting because of our 1-to-1 ratio. Using the ratio also allows us to calculate the amount of product that we have produced, which is a positive 0.160. And we put the positive number because that reminds us this is the amount that is produced. So if we had 0.1 of the hydrogen initially, and we have 0.08 reacting, we must have 0.02 of hydrogen at equilibrium. For the hydrogen iodide, we start with nothing. We have 0.16 reacting, so that must mean we have 0.16 at equilibrium. Now we can calculate the K values because we have got the amounts of each one of the substances at equilibrium. So let's calculate the K value. We've learned already that the equilibrium constant is the concentration of the products over the concentration of reactants. We square the hydrogen iodide because of the coefficient of 2 here that we have in the product. Now we substitute in our values. Remember, of course, we are using the values that we've got at equilibrium. So when we plug that into our calculator, we get 64. We have two significant digits because of the 0.20 moles per liter of the iodine at the beginning of the question. So therefore, K is equal to 64. Remember that K does not have units because it represents a proportion of the amount of products compared to reactants. Okay, let's try our second question here. Calculating concentrations at equilibrium. So in this case here, we are given our reaction, carbon monoxide reacting with water to make carbon dioxide and hydrogen gas. At a given temperature, our K value is 4.06, and we are told that we have 0.100 moles of carbon monoxide are mixed with 0.100 moles of water in a 1 liter flask. So in this question, they are giving us the K value, and they're asking us to calculate the equilibrium concentrations. So let's try this example and see how we do. So we are always going to use our ice chart for any equilibrium any equilibrium question. But before we even get to our ice chart, we have to first get all of our values in moles per liter. So we've got 0.1 moles of carbon monoxide, 0.1 moles of the water, and that's in a 1 liter flask. So let's calculate the concentration of both the carbon monoxide and the water. Now I've put that they're equal to each other because we have the same number of moles in the same volume. So we're going to take our number of moles and divide by the volume, just as we did in the previous question. We've been lucky here because they've both been a 1 liter flask. So we have our concentrations at 0.1 mole per liter. So now let's recopy our balanced chemical equation so that we can do our ice chart. So we've got the initial, the change in equilibrium. Initially, we know the amounts of our reactants. There's 0.1 mole per liter of the carbon monoxide, 0.1 mole per liter of the water. We're going to assume that we have no product initially. The reaction hasn't started. Now, we need to calculate the equilibrium concentrations. So we are going to need to let X represent something in our ice chart. Now, as a tip, it actually does make it easier if you let X represent something in the change row. You can actually let X represent whatever you want, but usually the math is easier to solve if you let X represent something in the change row. So I'm going to let X be the concentration of carbon monoxide that reacts. So that means under the carbon monoxide, I'm going to put a minus X value because I don't know how much of it is going to react. Using the ratio in our balanced chemical equation, we can get the rest of the values in our change row. If minus X reacts of the carbon monoxide, minus X will also react of the water because the ratio is a 1-to-1. And in our change row, we reflect that ratio. We can continue on looking at the ratios to get that X amount of carbon dioxide and X amount of hydrogen will be produced. We tend to put positive values for our products to remind us that they are produced. Now we can get the values at equilibrium for each substance in our reaction. 0.100 minus X for the carbon monoxide. We know this because we started at 0.1, we reacted X minus X, so at equilibrium we must have what we started with minus what reacted. The same philosophy holds true for our other reactant of water. For the carbon dioxide, we started with nothing, X reacted, so we must have X at equilibrium. Same scenario for the hydrogen. We started with nothing, X reacted, so we must have X at equilibrium. Now let's use our equilibrium expression. K is equal to the concentration of the products over the concentration of the reactants. In this case, we're given the value of K, so we're going to have 4.06 for our K value. The carbon monoxide and the water are both equal to 0.100 minus X at equilibrium. So I'm going to simplify right off the bat and make that squared, because we would essentially, oh, excuse me, ladies and gentlemen, I should be putting my products over. So we're going to have X squared because we have X amount of the carbon dioxide and X amount of the hydrogen. If we multiply them by each other, that's going to be the same as X squared. Our reactants are going to be 0.100 minus X. And because there are two of them, that's going to be the same as squaring it. Now, like we do in any of our math courses, we are going to simplify whenever possible. So let's look to simplify this equation. We're lucky here because we've got squared here and squared here. So we can square root both sides and get rid of our quadratic. So, taking the square root of 4.06 equals 2.01 and so on. Take the square root of X squared gives you X, and the square root of 0.1 minus X squared is just going to be 0.1 minus X. And now, using our good math skills, we're going to solve for this value of X. We have to get rid of the 0.01 minus X on the denominator here. So that means we have to multiply this by both things in our equation. So that means we're going to have 0.214944 minus 2.014944 X equals X. Simplifying further, I am adding this 2.01 to the 1x on this side, which gives me the 3.01. Now, solving for x then, we'll just continue up here. So our x is going to be equal to 0.06683. Now we're almost done, not quite. We need to get the equilibrium concentrations for each one of our substances in the equation. So let's calculate for the carbon dioxide and the water. It's going to be 0.1 minus our X value. So that is going to be equal to 0.100 minus 0.06683. So we're going to have a value here of 0.033 moles per liter. For the concentration of our products, they are equal to X. So they will be equal to 0.067 moles per liter with the correct number of significant digits. So this, ladies and gentlemen, represents the amounts that we have at equilibrium for all of our substances. Okay, our last example today is calculating the equilibrium concentrations, but having to use the quadratic equation. We were lucky here because we were able to simplify to get rid of the quadratic. In our next example, it won't be as easy. We are going to have to use the quadratic equation to solve for this. Okay, so calculating using the quadratic equation. So here's our reaction, similar to the one we had in the first example. Well, not similar, it's identical. And at a given temperature, the K value is 50. So they're telling us that we've got 2 moles of hydrogen and 1 mole of iodine, and they are in a 0.5 liter container. They are allowed to reach equilibrium, and we need to calculate the concentrations at equilibrium. Of course, we're going to use our ice chart, but before we do, we have to calculate the concentration of the hydrogen and iodine in moles per liter. So let's start off with the concentration of the hydrogen. Take your number of moles and divide by the volume. 2 moles of hydrogen divided by 0.5 liters is going to give us 4 moles per liter for the hydrogen. For the iodine, repeat that same calculation, except plug in the value for iodine. Now that we have both of our reactants in moles per liter, we can use our ice chart. So initially then, we have 4 mole per liter of the hydrogen. We have 2 mole per liter of the iodine. We will assume that we have no product initially. The reaction has not yet started. As we did in the previous question, it's usually easiest to let X represent something in the change row. So I'm going to let X be the concentration of hydrogen that reacts. So that means we're going to have a minus X value for the hydrogen, because that is the amount that is going to react. As soon as we know anything in our change row, then we can use the ratio from the balanced chemical equation to get the values for the other substances in the reaction. The ratio between the hydrogen and the iodine is a 1-to-1 ratio. So therefore, we are going to have X amount of iodine reacting. The ratio is a 1-to-1-to-2 ratio, so that would mean that we would have 2X of the hydrogen iodide being produced. At equilibrium then, for the hydrogen, we start with 4 moles per liter. We react X, so that means at equilibrium, we have 4 minus X. For the iodine, we start with 2. We react X, so we have 2 minus X. And lastly, for the hydrogen iodide, we start with nothing. 2X reacts, so we must have 2X at equilibrium. Now let's plug this into our K expression. So we are going to have our product, hydrogen iodide. Remember, we are going to square it because of the coefficient of 2 here, over our reactant. K is equal to 50. The hydrogen iodide is equal to 2X, and that will be squared. And the hydrogen, 4 minus X. And the iodine, 2 minus X. In our previous question, at this point, we were able to square root both sides. Of course, we can't do that here because the values for the hydrogen and iodine are not equal to each other. So we're going to have to simplify this equation and use the quadratic to solve it. So let's do that then. We'll FOIL out the bottom here. Four times 2 is 8 to give us the 8 here, and then we're going to have a minus 4x and a minus 2x, giving us a minus 6x altogether. Now we want to get rid of this on the denominator here, so that means we have to multiply both sides by these terms. So that means we're going to be multiplying 50 by 8, 6, and 1. I'm going to drop the zeros from this point on just to make it a little bit easier for our calculation. So we have 8 times 50 is 400, 6 times 50 is minus 300 because it's a minus 6. And 50 times x, so we get 50x. And we still have our 4x on the other side. Now we want to get it into the appropriate format so we can solve the quadratic equation. So let's have the x values we are going to collect up. We're going to have to subtract minus 4x on both sides. So that will give us 46x squared, because when you subtract 4 from 50, you get 46. 300x remains unchanged and the 400 remains unchanged, and that is equal to 0. So our a value is 46, our b value is minus 300, and our c value is 400. Now let's go ahead and use our quadratic equation. Your b value is a minus 300, so that'll be a positive 300 here. That is plus or minus 300 squared minus 4 times 46 times 400. All over top of 2 times 46. Now, if your calculator allows you to just plug in the numbers and solve it, please go right ahead and do that. If you do not have a calculator that allows you to do that calculation, you'll have to do it the old-fashioned way by plugging in the numbers. Now, we get two values when we solve for this equation. The first value that we get is 4.6528. The second value that we get, 1.8688. Now, both of these two values are, of course, possible answers, but we can eliminate one by looking back at our original question. Let's go back to our ICE chart. We've got 4.6 and so on as one possibility, or 1.86 as the other possibility. We can eliminate the larger number, the 4.6, because that is larger than the initial amount of hydrogen that we had. So we can't react more than we had. So as a result, we can eliminate this value. And this is the x value that makes sense. And in all of our questions, you will have one that you can eliminate. Now then, we will take this x value and solve for the values at equilibrium. The concentration of hydrogen, we said, was going to be 4 minus x. So when we do 4.0 minus 1.8688, our hydrogen value is 2.13 moles per liter with our 2 decimal places because we're subtracting, so we only use decimal places for our significant digits. For the iodine, (0.13 moles per liter). For our product, hydrogen iodide, that is equal to 2x. So that would be 2 times 1.8688, which gives us 3.74 moles per liter. So these represent our equilibrium concentrations. So that is it, ladies and gentlemen. Your homework will be in your booklet. The textbook questions will be given to you by the teacher on the day, and there are remaining questions in the booklet. So good luck.